Good evening, class.
Good evening, sir.
All right. Can you clearly hear me?
Yes, sir. Loud and clear, sir.
All right. Good. Thank you.
Yes, sir.
Class, let's continue our lecture. Last week, it was holiday. The last 2 weeks before last week, we discussed simple linear regressions. And you learn that for simple linear regressions, there are only two variables, one independent variable and one dependent variable. Both dependent and independent variable are numerical or continuous, right? With simple linear regressions, you need to have a clear objective and questions which you want to specify the effect of independent variable or dependent variable, or you want to assess the relationship between the two variables. So in order to find the effects of independent variable on dependent variable, you need to estimate the delta slope of parameter, or we call estimate or coefficient. All right. So you know what is independent variable, you know what is dependent variable, you know what is intercept, you know what is estimate. When we say estimate, it is the for sample, or we call slope of parameter, or in other words, we call it coefficient. So I try to use different term to make sure that you understand what I am talking about. All right. So delta an estimate for sample, or slope of parameter for populations, or in general we call it coefficients. All right. So with simple linear regression, you learn that OLS, which is the method to minimize sum of square residual, is one of the best method to construct delta 0 and delta 1. All right. So OLS minimize sum of square residual. You guys also learn how to interpret the estimate, the coefficients of independent variable on dependent variable. You also learn how to interpret the linear relationship between both variables by using non-log value. And also we explore the case of when independent variable or dependent variable is transformed to natural logarithms. We also discuss goodness of it, which is the R square. Right? You also learn this. We also discuss what is fitted or predicted value. So when we say fitted or predicted value, we refer to dependent variable that is computed from the equations. And the difference between the real dependent variable and predicted or fitted value are residual. Remember, we also have had a hand-on exercise in Stata on simple linear regressions, how to interpret it, how to construct residual and fitted or predicted value in Stata. All right. So class, this is just a brief recap from what we discussed in the last 2 weeks. on simple linear regression. Guys, if you don't review the textbook or lecture note before we move on, it is your choice. I'm not sure if you guys following me. So if you review what we studied, I believe that you guys follow or understand what I just summarized. All right. We also discuss the assumptions. All right. In order to say that OLS is the best estimator, when we say estimator, we refer that this is the model. Okay. When we want to make sure that OLS is the best model or the best estimator, we need to make sure that the assumptions are met. All right. If assumption 1 to 5 are met, OLS produce unbiased estimate, unbiased coefficient, unbiased slope. All right. If assumption 1 to 4 are met. But as we discussed, assumption number 4, zero conditional mean, is the critical issue, is the critical concern that simple linear regression by having one independent variable cannot hold. It's not met with the simple linear regressions. But you learn that if assumption 1 to 5 are met, all as produce unbiased estimate. If assumption 1 to 5 are met, all as produce unbiased standard error or variant. All right. If we obtain variant, then we can estimate standard error. All right. So OLS produce unbiased estimate and standard error or variant if assumption 1 to 5 are met. All right. So that's what we discussed from last week. But as you know, simple linear regressions are rarely applied in practice. Why? Because the zero conditional mean assumption is always violated. Meaning that when you only include one independent variable, some relevant variable that affect your dependent variable and correlated with independent variable are included in error term. So zero conditional mean is violated. So you cannot make Gaussian interpretations. You can only say, oh, there is a positive effect or negative effect based on the sign of the estimate. Today, we're going to discuss multiple linear regressions. Why do we need multiple linear regression? We will discuss it today. But before we move on, class, do you have any questions about simple linear regressions? Remember, class, to understand the lecture, you need to connect it to your research question and your objective. Remember, you want to estimate the effect of your independent variable of interest on Y. You want to know how much the effects, all right? Not simply the relationship, but I suggest you to formulate a research objective by specifying the relationship, because with either simple or multiple linear regression, which you will learn, you will know that you cannot make Gaussian interpretation. So I have my own agenda. All right. Any questions?
Yes, sir. Could you explain the assumption number 5 once more?
All right. Assumption number 5, which is homoscedasticity, right? And assumption number 5 appear in your quiz. Appear in your quiz 1. All right. Assumption number 5. Can you see the share screen? Can you confirm? Can anyone confirm?
Yes, sir.
All right. So assumption number 5 is homoscedasticity. So remember, our goal is to make causal interpretation. To make causal interpretation, what you just need to know now, we need to obtain unbiased estimate and unbiased variance or standard error. So to obtain unbiased variance and standard error, we need assumption number 5, homoscedasticity. So assumption number 5, it means that the variance of the regression functions is not conditional on any x. All right. So assumption number 4, zero conditional, means only look at the beta itself, meaning that the expected value of residual must be 0. But here we refer to variance. All right. Variance must be constant. What I say here is that the variance of u, so you know how do you construct residual. So variance is just the sphere of residual, and that sphere of residual must not be conditional on x. Not on x. It means that this variance here, if you look at this graph, is always constant. And when your x is increasing, here is an example of heteroscedasticity. So heteroscedasticity, it means that assumption number 5, homoscedasticity, is violated. As you can see here, when x, all right, when your x is equal 8, you have this curve, but when your x become larger and larger, the variance becomes, the distribution of variance become larger and larger, meaning that your residual or your sum, the sphere of residual is conditional on x. When x become bigger, the variance become larger. When x is smaller, the variance become small. So it means that your variance is not constant. So your variance is conditional on x. So assumption number 5 is to make sure that the variance is constant, not depending on x. Is that clear? So it is different from assumption number 4. All right. Number 4 is about expected value of the error term. It must be 0. Any other questions?
So it means that variance is not correlated with x, right?
Right. Whole variance must not, the variance that produced from the OLS must not correlate with x. In simple, that's correct.
Thank you, sir.
All right, it must be constant. Any other questions? All right. So let's move on to our new lectures on today we talk about multiple linear regressions. Wait a minute, let me extend the screen. All right. Before we do that, let me upload our new lecture note. I forgot to do it. All right. Wait a minute. Let me upload it now. So it is in general, in lecture notes and week 6. All right. So this is the week 6 lecture note. Okay. Class, now you can find week 6 lecture note in the folder of lecture note in general channels. All right, class. So today we're gonna discuss the multiple linear regressions. All right. But for multiple linear regression, we will divide into two parts. One is estimations. Another one is inference. But for this week and next week, we only discuss estimations. The following 2 weeks, we will discuss inference. All right, class. This is how multiple regression look like. So for simple linear regressions, we only have one x, right? But for multiple regression, as you see the term itself, multiple linear regression, meaning that this time you have more than one independent variable. So you have here is x1, but you also have x2, x3 until xk. All right. So delta 0 is still called intercept. Y is still dependent variable, explain variable, or response variable. Either x1, 2, 3, 4, independent variable, explanatory variable, or regressor, or so on. We still call this error term or disturbance. Any other variable that is not included in x are in u, in u, here we call it unobserved variable. All right. So delta 1, 2, 3 until k, we call it slope of parameter for population. All right. So the same, very similar to simple linear regressions, but here we have more than one independent variable. Remember, class, for multiple linear regression here, what we discuss is that both, again, dependent and independent variable, all independent variable are measured in numerical, right? Numerical variable, right? So they are all numerical variable, either y, x1, x2, or xk. They are all in number. All right. So why do we need multiple linear regressions? So as you know, with simple linear regressions, when we only have one x, the assumptions of zero conditional mean, the zero conditional mean is the expected value of u given x equals 0 is violated, meaning that error term is always correlated with x, right? Error term is always correlated with x. So we cannot expect that, we cannot prove that simple linear regressions, its error term is not correlated with x. So for simple linear regressions, assumption number 4 is violated. So in order to make sure that assumption number 4 is met, we need to incorporate, we need to include more independent variable. So that is why one motivation of multiple linear regression is to incorporate more explanatory variable into the model. So the goal is to address this issue. All right, the goal is to address this issue. But there are also other motivations when we use multiple linear regression. When we use multiple linear regression, we can also explicitly hold fixed other factor that otherwise used in U, meaning that when you include other independent variable into the model, then you can interpret as holding this factor constant. We will come to the example in a minute. You will understand this. But also the third motivation is that it allows you to use more flexible functional form. It allows you to use natural logarithms. It allows you to use what we call exponential quadratic functional form. So because one variable, you cannot use more flexible functional form. All right. So let's have a look at this great equation. Originally, we want to estimate the effect of this education on wage, right? We want to make causal interpretation between education on wage. But there are some variables that affect wage and correlated with education that we do not include in simple linear regression. So with this multiple regression, for instance, we can include another variable such as labor market experience, right? So here, assuming that we only have two variables and other factors are in other term. But now what we can say is that now we measure the effect of education explicitly holding experience fixed, meaning that we can compare the wage difference based on education by controlling experience, because we include right. Hopefully, by including experience in this model, assumption number 4 will be met. But for now, as you can see, we include more variables, and now we can interpret it by measure the effect of education explicitly hold experience fixed, or we control experience in our model. Right? This is the motivation of using multiple linear regressions. Understand the motivation of using multiple linear regressions?
Yeah, could you explain again the wage equation? Why do we hold experience facts?
Here is just the interpretation that the way. So normally, when we want to interpret the effect of education on wage here, when we include experience in this model, we can say that the beta 1 is the effect of education on wage. And here, experience is included in this model. So we say that the measure effect of education holding experience fixed or controlling experience. In other words, meaning that now you compare the wage of people, okay, the wage of two people that have different education but have the same experience when you include experience in this equation. So other variable that is not your variable of interest, meaning that you are controlling them, right? You're controlling the other variable. Your focus is only the effect of education. So in these interpretations, you measure the effect of education on wage. So in regression, we measure partial effect. When we say partial effect here, we only measure the effect of education, not both education and experience. No, we only measure the effect of education by controlling this experience. Is that clear? Understand?
Can we hold education facts?
All right.
Yeah, could you hear me?
Not if you want to hold education fake or whatever. What you want to interpret. If you want to interpret delta 2, you have to say that you measure the effect of You get what I mean?
No, sir. It was like from your side.
Right. I seem to have right now. Can you hear me?
Yeah, sir.
All right. Again, to answer your question, you can interpret by saying that you hold education fixed if you are interested in delta 2. If you are interested in delta 2, then you can interpret that way, meaning that you measure the effect of experience by holding education fixed. Can you hear me?
Yes, sir.
Right. So again, beside your estimate of interest, beside the slope or the coefficient of the variable of your interest, meaning that your interpretation, you hold other variable that you include in this model fixed, or in other words, you control that variable. You control that variable. In simple, the meaning is that now, for instance, if you want to measure the effect of education on weight, so you compare the weight between people who have different education, but they have the same experience. All right, that's what it's meant. That's what it's meant. All right. Next, here is another example. All right. Can you hear me, class? It seems I have bad connections. Can you hear me?
Yes, sir.
All right. All right. All right. So if it is not clear, please drop in the chat box if you don't want to talk. All right. So here is another example. All right. We want to estimate, for instance, the effect of student spending on average score. But here we have to control for family income. Class. Here, if you have a look at this example, if you do not include family income, your delta 1 here is biased. Why? Here, per student spending is likely to be correlated with average family income at given high school because of school financing. All right. So omitting average family income integration would lead to bias estimate of the effect of spending on average test score. Why? Because the ability to spend, how much you spend, is depend on your family income. Normally, students from rich household tend to spend more than students that come from poor household, right? So in simple regression model, the effect of per student spending would partially include the effect of family income on test score. What it says that in simple regression, if you exclude this average income, the delta 1 here partially include the effect of average family income. So for this multiple linear regression now, if you include this average family income, so here they have their own effects, right? So when you interpret this, you can say holding family income fixed or by controlling family income, the effect of per student spending on average score is this delta 1. Is this delta 1, right? So if you include, again, for simple linear regression, if you did not include average family income, this delta 1 is biased. Why? Because this delta 1 also partially include delta 2. We will discuss the effect of omitted variable next week. The effect of omitted variable. Are you following me?
So
Simply want now just yep. Questions?
So for the assumption number 4, zero conditional mean it to be not violated. We include every factor that affects x and y into the model, but why do we still need the other term in the equation?
In general, in writing, whatever you include, you cannot make sure that every variable that you included in the model totally explain your dependent variable. You cannot say that you include, for instance, 10 independent variable, but that 10 independent variable could not 100 explains dependent variable. That is why we always have regression. Error term. Why? It means that there are still some other factors that affect this dependent variable, but not included in the model. So whatever you run, you can try your best in the future. Whatever you produce, you will not have R square equal 1. Only when you have R square equal 1, that's when you say you don't need error term. But you can't have R square equal 1. Is that clear, David? You remember the meaning of R square, the interpret of R square? Right? What extent the model explain the variation of dependent variable? So for instance, if you include these two variables and you obtain R square equals 0.8, these two variables in this model only explain 80%. So other 2%, other 20% are in error term. All right? So we always have error term. We always have residue. So you cannot have a regression line that fit every point on the graph. All right. Next, here is an example that say through on the third motivation that you need more flexible form. For instance, in this example, all right, you use log salary, you also use log cell, and you also include quadratic function of CEO 10-year with firm. Meaning that it doesn't mean that when the CEO 10-year increase, they always have salary increase, but at one point the salary will no longer increase. So the effect will be something about what we call quadratic functional form. So at one point the salary will no longer increase when the 10-year increase. All right. So we use this square, this power tool. We call it quadratic functional form, meaning that at one point, even though you increase the CEO 10-year, it will not increase anymore. All right. But again, you will understand this from your own reading, from your own field of subject. When you do your reading based on your research question and objective, you will learn that on the paper use quadratic functional form or the other form as well. But again, our illustration here to tell you that this multiple regression allow you to use more flexible functional form. In this example, you can use quadratic functional form. All right. But remember, if you remember from simple linear regression, we say that this is multiple linear regression. But why here we have quadratic functional form? The term linear class, the term linear is only referred to linear in parameter. So what do we mean by linear in parameter? Linear in delta 0, delta 1, delta 2, delta blah, blah, blah. Not variable. All right. Linear in slope, linear in coefficient. You cannot have, for instance, delta 1 square. No, that is not linear. So you cannot use OLS. You cannot use ordinary least square. All right. So here, even with multiple linear regression, you can have different functional form as long as parameter is linear, as long as this delta is linear. All right. So don't be confused. When we say linear, we mean linear in parameter, not linear in variable. All right. Next, all right. So the same as usual, where is similar to the simple linear regressions. When we want to data is from random sample, so now we have multiple x. We have x1, x2 until xk, and only have one dependent variable, and we have n observations. We have n respondents, and as you remember, the regression residual here from the sample we write as ui hat, right? So it equals y1 minus the delta 0, delta 1 x1, delta 2 x2, blah blah blah, because of it from this regression or the original regression, right? So you want to find u. So when you rewrite to find u, then you get this equation. All right, that's regression residual. It's very similar to regression residual for simple linear regression, but for simple linear regression you only have one x. Now you have multiple x, and as you know, in order to find delta 0, delta 1, or delta 2 for all s, we need to minimize this sum of square residual. All right. So when you minimize the sum of square residual, then we will obtain delta 1, delta 2, delta 3 until delta k. But here, there is no clear mathematical equation here because it is complicated with multiple linear regression. But you can see it from simple linear regression. We have a clear equation for delta 0 and delta 1. And the way we construct this is quite similar, but for multiple linear regression, it's difficult. But with the application, a modern application such as theta, this slope, this delta will be constructed, will be computed by the modern application. All right. So the same rule, the same method when we use OLS to find delta 1, delta 2, delta 3 until delta k, we minimize sum of square residue. All right, we minimize sum of square residue. When we minimize sum of square residue, then we can find this intercept and slope or the estimate of the sample. All right, so the same, as long as you understand simple linear regression, we apply the same rule. All right, so the interpretation of multiple linear regression also the same as simple linear regression. So when you want to make an interpretation, you have to specify the x. So in other words, the effects of the variable is what we call partial effect. It's only the effect of your x of interest. So when we write xj here, this is what is xj? Xj can be xi, x1, x2, or x3. Okay, so here it depends on what is your estimate of interest. Bj can be Bi, B1, B2, B3, or B4. All right. So the interpretation is by how much that dependent variable change if j independent variable is increased by 1 unit by holding all other independent variable and error term constant. All right. This is the interpretation in multiple linear regression. This is the general rule. All right. So if you look at these interpretations, we want to make sure that all independent variables are constant. So when we control it, of course they are controlled. But error term, we cannot control it. All right. That is, we want to make sure that zero conditional mean assumptions are met. When we include other independent variable into multiple linear regression, of course we can say they are constant or they are controlled. But error term, something that we need to discuss, we need to address. So the multiple linear regression model managed to hold the value of other explanatory variable fixed. All right, fixed, as long as you include in the model. Even if in reality they are correlated with explanatory variable under consideration. All right. In reality, you cannot say they are fake, but when you input it or include it in the model or in the regression, the interpretation can say they are fake or they are controlled. Or add the variable, add the independent variable other than your independent variable of interest, and your interpretation say by holding other factor constant or fake or control, that interpretation are called ceteris paribus interpretations. It's called ceteris paribus interpretation. All right. So it has still to be assumed that unobserved variable do not change. When you include other explanatory variable into the model, you can say that, but again, unobserved variable do not change. This is something that you need to work on. You need to make sure that assumption number 4 and assumption number 5 are fake, because in interpretation, we have to make sure that unobserved factors that are in error term do not change as well. If the explanatory variable of your interest are changed, you want to say that if x1 increased by 1 unit, all other x constant also error term is constant, then blah blah blah. Right? This is the meanings and the interpretations in multiple linear regression model. Questions? All right. Next, here is an example. All right. All right. So here we want to look at grade point average at college, the effect of high school grade points. All right. So we want to know the effect of grade point from high school on the grade point average at college. But here we also control, or we also include achievement test score. So the interpretation is holding achievement test score fixed or controlling achievement test score another point on high school grade point average. Meaning that if you increase the high school grade point average by 1 unit, it is associated with another 0.453, the coefficient here, collect grade point average. So if the high school GPA increased by 1 unit, the college GPA is increased by 0.453 by holding ACT fixed. So in this model, we holding ACT fixed. In fact, we also say that holding unobserved variable fixed, but it is difficult to prove this. All right, following me? In other words, or in simple, in an easier way of interpretation, or if we compare two students with the same ACT, you see, when we include ACT here, we mean that we control it. We want to hold it fixed. Or in other words, if we compare two students with the same ACT, with the same achievement test score, but the high school GPA of student A is 1 point higher, we predict that student A to have collect GPAs that is 0.453 higher than of student B. If there are two students, they both have the same achievement test score, but A have high school GPA 1 point higher than B, then it is expected that A will obtain collect GPA 0.453 higher than B. Following me? This is the interpretations of multiple linear regressions. All right. Or if you are not interested in high school GPA, interested in high school GPA, you can say holding high school GPA fixed. If achievement test score increased by 1 unit, college GPA is increased by 0.0094, right? So it depends on what is your independent variable of interest. Right? Next. So remember, this is the property of OLS. It's the same as simple linear regressions. Here we still call it fitted or predicted value, meaning that if you want to compute new y based on the equations, when you find delta 0, delta 1, or delta 2, then you can compute it. We did this in Stata the week before last week, right? And then you can calculate residual. In Stata, you can predict residual or you can manually by using this equation. I did both, right? I show you, I illustrate how you can get residual from predicted functions and how to manually compute it using these equations. All right? Hopefully you review what we discussed the last 2 weeks before the holiday. All right? So as usual, the property of all regressions is the same as OLS. So the sum of error term, we want it to be 0. All right, it's 0. And we want to make sure that residual has nothing to do with x. All right, because in multiple linear regression, we have multiple x, so we write xij, meaning that more than 1x. So make sure that here the residual here is not correlated with x. So the relationship between x and u here, the summation of the relationship between x and u here should also be 0. All right. So and then we will get this. This is the mean. All right, the mean. So the sample average of y of the regression lie on the regression line. All right. That's the same as simple linear regressions. Then we discuss goodness of fit. All right, that's the same rule as the simple linear regressions. So we have here this composition of total variation. We have SST equal SST plus SSR. If you do not remember, I put it here. SST is here is the y minus y bar. Where is y bar? Y bar is this one. Okay, from this one, and then y hat. What is y hat? Predicted or fitted y minus the average y square. This is the SSR. What is SSR? Sum of square explained. Sum of square total. What is SSR? Sum of square residual. All right. So in order to find R square, simply SSE divided by SST or 1 minus SSR divided by SST. The same. All right. And you also learn about you also know the interpretation of R square. The interpretation of R square. All right. Let me move next. Then let's try to interpret here the first multiple linear regressions. All right. Here, if you look at this example, we have number of time arrested in 1986. So here, sorry, the example explaining the arrest record. All right. So number of time arrested, 1986. Proportion of prior arrested that lead to convictions, month in prisons, quarter employed. All right. So here we have R square and we have ends. So meaning that in these regressions, there are 2,725 respondents. This model, the model that includes 3, here as you can see, this is H1, this is H2, This is X3, right? The model that have 3 independent variables only explain variation of dependent variable 0.4, which is equal 4% points 13. So here, when you have multiple independent variables, this model could only explain 4.13% of the variation of independent variable. There are about 96% that could not be explained. They are included in error term. All right. Now have a look at our interpretation. An increase in proportion of convictions, this one. All right. Lower predicted number of arrests, right? We can say holdings, month in present and quarter employed fixed or constant. So a longer present term lead to lower predicted number. Here is it. Longer present term here, lower predicted number of time arrested. So first you can look at the sign of the estimate. Question everyone? I go a little bit fast because the last few slides, they are the same as simple linear regressions. So we spend more time on the example. Questions?
Sure. Did you hear me?
Yes.
For example, we include many independent variables into the model, but our square only explain, for example, only 30%. In this case, can we still make casual interpretation?
All right, let me get back to the point. We did highlight this we will highlight this. Elsewhere has nothing to do with causal interpretation. Elsewhere has nothing to do with causal interpretation. You can make causal interpretation as long as you obtain unbiased estimate and unbiased standard error. And let me tell you that those who are not in economic field, in applied econometric field, they tend to pay attention to R-square. But for economists like me, we pay attention to estimate. We want to obtain unbiased estimate and unbiased variance so that we can make causal interpretation. Now, assuming that you want to evaluate public policy, for instance, my research, I aim to evaluate the poor identification program in Cambodia. So we don't care to what extent our model explains the variation of dependent variable. What we care is make sure that the estimate of the policy variable, the estimate, the coefficient of the policy variable is unbiased. Even though we have low R-square, it doesn't matter. R-square, let me say it now, is only important for those in social science or basically for those who are doing machine learning. You may not know what machine learning for now, but you may understand it in the future. So again, for us, economics, applied economics or applied econometrics, we care about unbiased estimate and unbiased variance that we produce unbiased standard error, so we can make causal interpretation. It has nothing to do with R-square. Good question, David. We will highlight it either today or next week. Is that clear? So yep.
So in multiple linear regression, the square assumption still apply, right, sir?
Again, it depends on your own reading. We will discuss this later, the assumption. There is a change a little bit about assumption. We will discuss it today and also next week. You will see it in the next few slides about the assumption. There are a little bit change on the assumption because in simple linear regression, we only have X. But now the assumption are slightly changed. We discuss that later, David. Got it?
Yes, sir.
All right. So next, here is another example. Here another the same example. I'm sorry, but here we add more variable. Here, if you look at this regression, we only have 3 dependent variable. All right, and we obtain this R square 0.413. Here, when we include another independent variable, R square increase very slightly from 0.41. Now it becomes 0.422. R square increase only slightly. Okay, so again, here the interpretation is the average. Okay, average sentence prior to convection increase the number of arrays, right? But here you see limited additional explanatory power as R square increase a little. R square only increase a little. So that's reply to your questions. General remark on R square. Even if R square is small, as it is given in the example, regression may still provide good estimate of ceteris paribus effects, meaning that you don't have to care about R square. You need to make sure that the assumptions are met to make causal interpretations. All right? It doesn't matter whether R square is small or large, but the causal interpretation depends on the assumption. And only you know whether there are some variables that omitted or included in the error term. We will discuss this more in next week. You know what are the effects of excluding some relevant variable. All right, let's get to the assumptions that David asked earlier. All right, so in multiple linear regression, assumptions slightly change. So assumption number 1 here, again, very similar, linear in parameter. Because we use simple linear regression, we need to make sure that our delta are linear. All right, so if X is allowed to be linear or non-linear, but as long as your parameter is linear, you can use OLS. All right. Assumption number 2, random sampling. You already know X and Y are randomly collected from random sample. The data is random sample drawn from populations. All right. So these 2 assumptions are the same as simple linear regressions. All right. But now we have assumption number 3, which is different from assumption in simple linear regressions. By the way, class, can you hear me? Because now it is raining from my side in my area.
Yes, we can hear you later.
All right, thank you. So class, this is a new assumption. So assumption number 3, by the way, when you see MLR3 here, class, it means multiple, all right, linear regression. So assumption number 3 now is, this is the new assumption for you guys. It's say no perfect collinearity. What do we mean by no perfect collinearity? No perfect collinearity meaning that in multiple linear regression, you include more than one independent variable, right? You include more than one independent variable. So since you include more than one independent variable, the assumption number 3 is that there is no perfect correlation between 2 independent variables. All right. So in sample here, in sample, none of independent variable is constant, and there are no exact relationship among independent variable. I will give you the example next. All right. What do we mean by? Let me give a remark on assumption number 3, class. So assumption only rule out perfect collinearity. So what do you, if you don't know what is collinearity, it means correlation. You already know what is correlation is. So what it says here is that the assumption number 3 does not allow two variables to have correlation equal 1 or -1. You remember when we discussed about correlation, the perfect positive correlation equal what? Perfect negative correlation equal -1. So in assumption number 3, it does not allow independent variable to have perfect correlation. All right, so it allowed to have correlation but not perfect. The correlation must not equal 1. All right, so again, it does not allow perfect correlation between explanatory variable, but it allows for imperfect correlation. All right, as long as it is not perfect, it is not 100%. So if an explanatory variable is in a perfect correlation of another explanatory variable, normally the applications or the way to address the issue is to omit, to drop one independent variable out of the model. For example, you have two variables and they are perfectly correlated, x1 and x2. The way to address it is to drop or to delete one variable from your regression model. All right, that's what we mean perfect collinearity. Here's an example of perfect collinearity with small sample. So class, for instance, I conduct an interview with you guys about, for instance, I want to estimate the effect of expenditure on average score. But I also want to control for income. All right. So it might be the case that, all right, when I ask you how much is your spending, you say 100. How much is your income? So because you are a student right now, let's say you do not have any part-time, all the source of your income are from your parent. So if your parent give you 100 USD, you spend it all. So in this case, if every one of you, say for instance, now there are 30 students, if every one of you obtains, for instance, 100 USD, and you also spend 100 USD, you see, in this case, expenditure and average income perfectly correlated. When you get 100, you spend 100. When someone gets 50, you spend 50. Because you are a student, you do not have any saving, right? So in this case, both variables perfectly correlated, all right? So in small sample, average income may accidentally be an exact multiple of expense, all right? Or in other words, some of you may say, all right, if you get 100 from your parent, you spend 50, all right? If you get 50, you spend 25. You see the correlation here is 2 times. So they are perfectly correlated. So as long as you get 100, you spend 50% of your income. That means that they are perfectly correlated. All right? So all of you do the same. That is why your data resulted in perfect collinearity. Following me with the first example, what do we mean by perfect collinearity with the assumption number 3? All right, so let me move to another Example, another example of perfect collinearity is the relationship between two regressions. For instance, all right, you want to estimate the effect of the share on campaign, all right, the share on campaign on the number include the variable A is the share that they spend on campaign, and share B is the money they spend on other activity. So share A both with share plus share B equal 100. So in this case, if you include both share A and share B, there is a multicollinearity because these two variables add up to 100. If you run regressions, your regression will automatically drop one variable. This is another example of collinearity. Because here, if you know that the share A is 10%, you automatically know that share B is 90%. If you know that share A is 5%, you know that share B is going to be 95%. See, this is another example of perfect collinearity. Get what I mean? What do we mean by perfect collinearity? This is the new assumption, and make sure you guys understand this. Because in multiple linear regression, we employ more than one independent variable. So we have to make sure that your employed independent variable are not perfectly correlated. All right, are not perfectly correlated. When we come to data exercise, I will give you an example of this perfect collinearity. I will try to find a data so that you can have a look, and then you can try to estimate the correlation. What do we mean by perfect collinearity? But next week you will hear another term which is very similar and confused to perfect collinearity. But now make sure you guys understand what do we mean by perfect collinearity. Question, everyone? Can you follow me? So now you see a new assumption. A new assumptions. All right, next. So assumption number 4 is the same as simple linear regressions. In simple linear regression, we also have 0 conditional mean, but we only have one x. But now the expected error term given x1, x2, x3, hopefully they are equal 0. Meaning that all relevant variables that affect, dependent, and correlate with x is not in error term. So there is no correlation between error term and employ independent variable. So all relevant variables should be included in the model, not left in the error term. All right. So hopefully you guys know what is 0 conditional mean by now. So in multiple linear regression model, 0 conditional mean assumption is much more likely to hold. Why? Because we have fewer things end up in error term. We incorporate more independent variable, unlike simple linear regression where you have only one independent variable. Okay. Here, for example, all right. Here we want to estimate per student spending on average test score by also including average family income. So if average family income was not included in the regression, this variable will be up in this error term. All right, if we do not include it here, it will be up in error term. So it would then be hard to defend that per student expenditure is uncorrelated with error term. If this average income is included in error term, then you cannot say that per student expenditure is not correlated with error term, because you know that spending is correlated with income. And if you do not include income in this model, if in error term, then 0 conditional mean is violated. But now, since you already include every income in the model, You might say that, oh, now zero conditional mean is mid. All right? That's what we mean by zero conditional mid. Question, everyone? Questions? How are you? All right. So from the multiple linear regression assumption 1 to 4, what you find is new is assumption number 3, perfect collinearity or perfect correlation. All right. So now we have another term what we discussed. All right. So discussion on zero conditional mean assumption. All right here. So if explanatory variables that are correlated with other term are called endogenous. All right, endogenous. If your variable of interest, all right, correlated with other term, we call it endogenous variable. And that issue of endogenous variable, we call it endogeneity. And that endogeneity is a violation of assumption number 4. So next, I will say zero conditional mean endogeneity. So it means the same thing. Meaning that when we say endogeneity, zero conditional means assumption is violated. All right? It means that your variable of interest is endogenous, meaning that it is correlated with other term. So guys, you need to understand and remember the term. However, if explanatory variables are uncorrelated with other term, we call it exogenous, meaning that assumption number 4 is whole. All right, so there is no problem of zero conditional mean. If there is an exogenous variable, there is no problem with zero conditional mean. All right, so again, endogeneity is the key assumption of causal interpretation. All right, so everyone, if you want to ask me again, do we make causal interpretation? Zero conditional mean endogeneity is the important assumption for making causal interpretation of regression for unbiasedness of OLS. See, assumption number 4 is the most important. All right. So if assumption number 1 to 4 are met, we believe that the expected value of the estimate that we constructed from the sample equals slope of parameter. All right. So we obtain unbiased estimate. We obtain unbiased estimate. All right. So for any value of population parameter, in other words, the OLS estimate are unbiased estimator of population parameter. The same rule, the same assumption. All right. Any questions? Any question, class?
No question yet. Yeah.
All right. So it is time for break, everyone. It's now 6:50. As usual, let's have 30-minute breaks. So please return back to the room at 7:21. Your 30-minute break start now. I see you after break. Hello, class. Are you here?
Yes, teacher.
All right. Before we continue, does anyone have any questions about the first part of estimation for multiple linear regressions? Any clarifications? No? All right. By the way, for homework on week 5, I didn't see the submission from group 5. We only have group 1, 2, 3, 4, 6, and 7. Group 5 did not turn in the paper in week 5 assignment yet. All right. I reviewed the submitted paper, class. I found that the paper that some groups selected may not be suitable for your level. So it is up to you. It is up to your group decision if you would like to stick to your selected papers. But I would suggest you guys to discuss with your group and to select the paper that may help you to understand more about regressions. All right. So what I am going to do next now is to request everyone to work in group. All right. So you guys are requested to work in group to discuss about the selected paper and to make any arrangements to prepare your slide for 10-minute presentation on the selected paper. So in short, you guys are requested to work in group, discuss with your group, and summarize the selected paper. And again, you are free to change the selected paper. But because I found that some paper are difficult for you to understand. All right. So time is now already 7:26. Please have a group discussion until 8:00 and return back to the big group at 8:00. Please discuss with your group on the paper, allocate the task or any arrangement, make 10-minute presentations, and please submit your slide in the assignment folder in PPT format before next week lecture. So just let's say your 30-minute discussion start now. As usual, please use the group channel in our Microsoft Teams. All right? Your group discussion start now, everyone. If you have any questions, you can clarify with me or call me anytime. I am here for you.
Hello, teacher. Hello, teacher.
Sorry, I forgot to mute. Go ahead.
Teacher, because I was late, can you tell me again what we're gonna do now?
All right. What we are going to do now is to do a group discussions for 30 minutes. Discuss with your group to discuss and summarize the selected paper that you turn in on week 5. Prepare 10-minute slide presentation. And you need to submit it in the assignment folder week 6 before next week lecture. But now, do the group discussions, discuss about the paper. But again, you are free to change the paper because I found that some paper are difficult for you to understand during your current level. All right, so you are free to change the topic. But now, just discuss and make 10-minute presentations. Submit it before next week. Clear?
Yes, like so after this discussion, we have a presentation 10-minute, right? Each group, right,
It will
teacher,
be
or
next
what?
week. It will be next week.
On next week. So
Right,
today
right.
we just have a discussion, right? Like
Right. You discuss among
Okay.
your group member to understand the overall content and who responsible for what, and submit the slide before next week.
Okay, thank you. Like
Hello, sir. Group is here, sir.
You need to have a group discussion by now.
Yes, sir. We discuss on the Telegram channel.
I would like to suggest your group to use our group channel, group 6 to do the discussion.
Yes, sir. Yes, sir.
Monitor the progress.
Hello, teacher. Hello, teacher.
Group 1, are you here? Group
We are here, teacher.
All right. Group 2. Group 2. Are you back?
Here, teacher. We're back.
All right. Group 3. Hello, Group 3. Group 3 is still in discussions. Group 4.
Yes, teacher.
All right. Group 5.
Yes, teacher.
All right. Group 6.
Yes, teacher. Yes.
All right. Group 7.
Yes, teacher.
All right. So only group 3 is still in the discussion. Let me call them. Group 3, are you here?
Yes, lecturer, yes.
All right. Thank you, Timur. All right, everyone. So every group is back in the class now. So after your group discussions, folk, do you have any question to clarify? So during the discussion, I did join some group, almost all group, except one group that ended a little bit early. So does anyone have any question or clarification you want to ask?
Lecture for group
Yep.
1, we change the paper. So do we need to upload it again to the homework?
It is selecting from the side, Nita. So you mean that your group changed the paper?
Yes,
So
yes.
it is okay to change the paper. Just replace the new paper in the last week assignment, the week before last week assignment. Is that okay? Just replace the paper. That's okay.
Yes, teacher. Yes, thank you.
Right. Any other questions? Any questions after your group discussions?
Sure. Before you talk about want us to explain about the regression, can you clarify about that? Sir?
Oh, no, I do not want you guys to explain the regression. But what I said is that it is better if your group could select the paper that uses regression. Why? Because I want you guys to relate the paper to our lecture. Otherwise, you have different assignments and different lecture. So when your group select the paper that uses regression, then you can relate to what we discussed. All right. For instance, now we discussed about endogeneity, the zero conditional mean. We discussed about causal interpretation. Then you may find that in that paper, when they use multiple linear regressions, they may say that they cannot make causal interpretation. They want to address the issue of omitted variable. So they may mention something that quite related to our econometric class. Do we answer to your questions? Put down.
Yes, sir. Sure, but in my paper, they don't use the word variable. They use the word variant here.
No, variant is different. So variable is independent variable or dependent variable. The variant is where is the dual. All right. You remember when we discussed the assumptions to obtain unbiased estimate, we need to make sure that assumption 1 to 4 are met. Assumption 1 is linear in parameters. Assumption number 2 is random sample. Assumption number 3 is no perfect collinearity. Assumption number 4 is zero condition. And bias variant or estimate we need homoscedasticity. When we say variant, we mean sphere residual, and that sphere residual must not conditional on X. It means that the variant has no correlation with explanatory variable. So variant is another term. It is not the same as variable. So the paper may want to mention that they want to address the issue that related to variant. You got what I mean, Udam? So
yes,
you may need to, all right, you may need to review the lecture a little bit. So next week, if you have any questions, you can clarify with me again. I am happy to answer your questions if you guys review the textbook, review the lecture note. But I am afraid that many of you did not review the lecture note. Any other questions?
No, sir.
All right. So let me wait a little bit. If some other folk may have any other questions from the group discussions, or you probably have some reflection you want to share.
So for the replace paper, we had to delete the old paper, right? And
Right. You need to turn in the new paper and replace the existing one so that I can see the update, right? Because during your presentations, for instance, next week you will need to present, and at the same time I will review the paper so that I can explain you more. For instance, if you mention something so that I can relate to the paper. Otherwise, I do not have paper to read. I cannot help you to explain some difficulty that you may face during your summary, during your group presentation preparations. Probably some of you, when you are doing your preparing your slide presentation, you may find something new and you want to ask me. So if I have that paper in that folder, then I can refer to paper, then I can have to answer your question. All right, Sunita.
Let's have we replace the one in week 2, right?
No, in week 6, in week 5, the latest one. Don't worry about the previous one. Week 5.
So we need to answer like all the question, what type of data, something again, right?
All right, let me clarify this. Class. All right. Class, the previous homework was done. All right. You don't have to revise your previous homework. Previous homework, I asked you guys to do something. Don't care about that. You just need to focus on the new homework. But for those groups who have not submitted the old homework, you need to do so. Because your score is rely on your homework. All right. I have to check and then I do the score. Some groups have not submitted, like I highlighted earlier. All right. But because you need to do presentation, I need some paper to base on. I need some paper to read. And the assignment week 5 was I asked you guys to submit your selected paper. But next week, if you present a new paper, if you do not replace the existing one, how can I read the new paper? How can I have to answer some of your questions that you may have? That is the idea. All right. So you don't have to do the last homework. Just replace that so that I can have paper to read. All right, to read, to understand your presentations. Clear, Sunita?
Clear, lecturer. Thank you.
All right. Let me explain again, because some of you may not pay much attention to what I said before the group presentations. Some of you may pay attention, but you don't fully understand. When it comes to your work, you pay more attention. That's normal. All right. So class, the purpose of the group discussions is to ask you guys to summarize the selected paper into the 10-minute presentation. All right. And you need to submit your slide in the assignment week 6 before next week lecture. So again, I will not write any announcements. All right. I expect that at least a group member your member attended today's class. All right. And again, when you're preparing your slide presentations, I believe that you may learn something from the paper. So in order to be beneficial for your own learning and your group assignments, I said that it is important that your selected paper employ multiple regression. Why? Because here we learn about econometrics. So that you can relate your selected paper with the lecture. This is the first goal. The second goal is that by the end of this course, you guys are going to write group assignment. All right. So when you prepare when you do the reading and when you prepare slide presentation, you will see the structure of the paper. You see the method, you see the introduction, so that you can adopt that style into your group assignment. And also, you may adopt similar method, variable, data in your group assignment. So by reading, by preparing, by discussing with your group to prepare this 10-minute presentation, you could also have a better understanding and relate it to the lecture and also beneficial to your group assignment. All right. And again, you have to submit the slide before next week lecture. 10-minute presentation only. Any other questions? No? All right. Just a note. I will not select all group to present next week. It depends on time. So from next week, I may select one group, two group, or three group, or four group. It depends on time. All right. Because in a week, I cannot do the lecture for the whole session. You guys are not paying attention to me. Some of you guys are playing game along the way with the lecture. So I want to change the atmosphere. All right. So sometimes we have group discussion, sometimes we have presentation, so that your brain can relax. And also we can connect from the application with the theory. So again, from next week, I may select 1, 2, or 3. The remaining we'll need to present the following week, and so on. That is the idea. All right. Any other question about? Yep. Go ahead, Kim Hua.
Sure. Yes, lecturer. So just want to clarify a little bit. So for our paper, the model have to be the multiple linear regression, right? Not simple linear regression.
Normally, I don't think you have any paper that use simple linear regression. I don't think.
I actually.
Is that
lecturer, but I saw
use simple linear regressions?
Yes, lecturer. I saw a paper. Actually, it's the paper that we selected.
Now, it's okay. Now let me ask you, what type of data they use? Do they use time series data?
I'm not sure, lecturer.
All right. You can present it. Don't worry. It's up to you. But again, it doesn't mean that simple linear regression is not practical. But it depends on the nature of the data. What we discussed up to now, we are now on week 6. We only discuss econometric model, simple and multiple linear regression for cross-sectional data. But if they use, for instance, the time series data, they may call it linear regression, simple linear regression, but they use another method. All right, it depends on data. But if they use cross-sectional data, I don't think they should employ simple linear regression. That doesn't make sense. Or meaning that the paper is very bad quality. But let's see, you can present it. Don't
yes, lecturer.
All right. Any other questions?
Yes, lecturer. Thank you.
All right. All right. That is all about group presentation. But before we close today's session, class, allow me to recap what we discussed. So today, I bring you guys to a new topic, which is multiple linear regressions. All right, if you don't remember much, don't worry. Take note the equation. But try to follow my recap. I only recap the main point. If you understand this main point, it is good enough for you to do your group assignment, because everything is based on data application. All right, why do we need multiple linear regressions? There are three main motivations, but the first main motivation is that we want to address the issue of zero conditional mean. Zero conditional mean. Why do we want to address the issue of zero conditional mean? We want to make causal interpretation. What do we mean by causal interpretation? In simple, we want to interpret the number of coefficients. I give you an example. For instance, you want to assess the relationship between wage or education and wage. If you cannot make causal interpretation, you only interpret the sign. If you found that education has positive sign, the coefficient is positive, you only say that education has positive effect on wage, but you don't interpret the coefficient. Why? Because it does not allow you to make causal interpretation, because zero conditional mean is violated. All right, you do not interpret the sign. You only say there is a positive relationship between education and wage, or wage or education has positive effect on wage. If you want to make causal interpretation, you say, all right, if education increased by 1 year, wage increased by that much. That causal interpretation is the main goal for most applied economists or applied econometricians. For instance, my research, I want to know how much the poor identification program or policy in Cambodia have to reduce health spending for Cambodian people. I want to know how much. All right, not just saying that, all right, I found that poor identification program or policy Cambodia reduce health spending. Everyone logically could say that, but as economists, I want to know how much. All right, how much, to what extent? So causal interpretation want to interpret this magnitude, the number of the coefficient, not only the sign. If you cannot make causal interpretation, you only say positive or negative effect or relationship. All right, in simple term. All right. Again, if you want to make causal interpretation, you need to make sure that zero conditional mean is met. But in fact, if you want to make causal interpretation, you need to make sure that your estimate is unbiased, meaning that assumption 1 to 4 are met. Also, the variance is unbiased, so that you have unbiased standard error. So assumption 1 to 5 need to be met. Following week, we will discuss hypothesis testing. And that hypothesis testing, we need unbiased estimate coefficient and unbiased standard error. All right, that is all for today, class. But you remember that we use multiple linear regression because we want to address the issue of zero conditional mean assumption, or we call it endogeneity. All right, that is the new term, endogeneity. Right? Any other question about today's lectures or group discussion before I close today's sessions?
When do we have data session?
Oh, after, for instance, we will have data session only when we finish the multiple linear regression, so that I will give you a hands-on exercise on multiple linear regression.
Lecturer, I have another question.
Mm-hmm. Go ahead, Kim Hua. We'll get
Hello,
back
lecturer. Can you hear me?
Yes.
Yes, lecturer. So for the presentations, do every member of the group have to present, or just a few or one?
It depends on your own arrangement. You can have multiple or one. It's up to you, because we only have 10 minutes.
I see.
Right.
Got it. Thank you, lecturer.
But it is important. You guys, only your group know who actually prepared the slide. I don't know. Let's be honest, I don't know. It is up to you. For those who are inactive member, it's up to you. Remember, if you join less, if you participate less, you benefit less. All right. So all right, everyone, Kim Hua, it is your arrangement. Either you want to have every member to present or only one member to present. But again, if you have everyone to present, make sure you have a connection. All right. Good.
Yes, lecturer.
Question, Kim Hua.
Yes.
All right. Get back to Navin. Navin, you want to have another questions?
No, sure. Thank you.
All right. If there is no other question, class, let me close today's session. Remember, I will not write any announcement about our homework. Remember your homework. Submit it before next week. And for those groups that have not turned in or submitted the previous assignment, have a look at the assignment folder. If you don't submit it, you know the result. That is all for today, class. Happy holiday. Happy water festival. Stay safe and take care. Enjoy your holiday. Bye-bye. See you next week. Bye-bye.